All right, let's talk about a force that you've absolutely felt, but maybe never really, thought about. It's a thing that makes your hair stand up, lets a balloon stick to the ceiling, and yeah, gives you that little shock when you least expect it. We are diving into the world of static electricity. I mean, we've all been there, right? You're walking across a carpeted room, you reach for the doorknob, and zap, you get that little jolt. Well, that tiny spark is our way in. It's the most common example of a phenomenon that actually causes huge problems for some major industries. So, what is this stuff, really? Well, the sciencey name for it is frictional electricity, and that name kind of gives the game away. It's an electrical charge that builds up on something, usually because of friction, and the key word is static. It just sits there, waiting for a chance to discharge.
Now, to really get what's going on, we have to zoom way in, like down to the atomic level. We're going to crack the code and find out what's actually happening to create that zap.
For the longest time, scientists had some pretty wild theories. Some thought it was this invisible fluid moving between things. It was a good guess for the time, but the real answer was much, much smaller. The breakthrough was realizing it's not a fluid at all. It's about tiny, tiny particles.
And here's the secret. It's all about electrons. See, everything, your socks, the carpet, the doorknob, is made of atoms. And atoms normally have a perfect balance of positive and negative charges. But when you rub two things together, you can actually knock some of those little negative electrons loose, and they jump from one surface to another. It's like a little electron shuffle.
And this shuffle really only has two possible outcomes. Super simple. The thing that gained extra electrons, it's now negatively charged. And the thing that lost them? Well, it's now positively charged. That's it. That imbalance is the heart of static electricity.
So a little zap from a doorknob, no big deal, right? But what happens when this electron shuffle is happening on a massive industrial scale? Well, the problems get a whole lot bigger than just a tiny spark.
And it all comes down to two very basic rules you probably learned in science class. Opposites attract, and similar charges repel. This isn't just a textbook concept, though. In the real world, these two laws can cause absolute chaos.
Just look at the textile industry. When fibers all get the same charge, they push away from each other and poof, they balloon out, making them a nightmare to handle. And attraction is just as bad. It can cause parachute material to stick to itself so it won't open, or it can make dust and dirt literally cling to fabrics, creating these ugly stains called fog marking.
Okay, think back to that doorknob zap again. Annoying, sure, but get this. That tiny little spark, it can be the result of a charge of over 10,000 volts. That's a massive amount of potential energy just sitting on your body. And in a factory, that number can get way, way higher.
And that's when things go from just being annoying to being flat out dangerous. A single spark near flammable materials could cause a fire or even an explosion. People can get seriously painful shocks, and even if nobody gets hurt, that static charge can ruin products by making them stick to machines, messing up the whole production process.
So with all this on the line, you can't just guess, right? How in the world do you measure an invisible force like this before it becomes a disaster?
Well, they use this really clever device called a Faraday cylinder. It's pretty cool. You just pass the charged material, like a piece of fabric, right through the cylinder. That induces a charge inside the device that can be measured with incredible precision. It basically makes the invisible visible. That measurement then gets plugged into the simple formula, Q equals C times V. Basically, by measuring the electrical potential, or voltage, that's the V, they can figure out the exact amount of charge, which is Q. No more guesswork. It turns a vague problem into a hard number they can work with.
And here's the most important part. Once you can measure a problem, you can start to solve it. So let's look at the toolkit engineers use to actually tame the spark and get static electricity under control.
And they have a whole bag of tricks. Sometimes just cranking up the humidity works, since moisture in the air helps the charge dissipate. They can use special oils or apply anti-static chemicals. A really common one is just grounding the machinery, giving that extra charge a safe path to the earth. They can even ionize the air or weave special conductive fibers right into the material itself.
Okay, so we've gone from a tiny personal zap all the way up to massive industrial machinery. Let's bring all this back home and think about how this force is at work all around us, every single day.
So really, the next time you pull laundry from the dryer and that one sock just refuses to let go of your sweater,
Or you feel that familiar spark from your car door. Just pause for a second. Now you know what's happening under the surface. What's really going on there?
It's the electron shuffle. It's that simple. The very same tiny force that makes fibers balloon out in a factory is the exact same thing that's making your clothes cling. Your little, everyday annoyance is just a miniature version of a giant industrial challenge.
And that's really the big idea here. Static isn't just some random quirk. It's a fundamental force. It connects everything from a clinging sock to an industrial explosion, all the way up to a bolt of lightning. It's like an invisible architecture shaping our world. And now you know how to see it. Thanks for tuning in.